Hi, welcome to the next video. Let's continue where we left off. So last time we were talking about a standard normal random variable and how table 3 in appendix C you can use to find the values of that random variable. So today we're going to talk about, we're going to go further into that topic. So first, if x though is a normal random variable, with parameters mu and sigma, then z is x minus mu over sigma is a standard normal random variable. Okay. So we're starting here with a normal random variable with parameters mu and sigma. Okay. So if x is a normal random variable with those parameters, then z, which is x minus mu over sigma, is a standard normal random variable. Okay. So a normal random variable is one such that mu is equal to 0 and sigma is equal to 1. Okay. So here, sorry, the other way around. A standard normal random variable, the word standard here, what the word standard there says is that mu is 0 and sigma is 1. And so that is a normal random variable such that mu is 0 and sigma is 1. And so if you start with just x, which is a normal random variable, not necessarily a standard one, then if you define a new random variable z as x minus mu over sigma, then z is a standard normal random variable. The mu for z is 0 and sigma for z is 1, right? Mu is the mean and sigma is the standard deviation. Okay, but those are just the parameters of it. Okay, let's keep going. Okay, so thus, to find the probability that a is less than x less than b, we do the following. So we're going to take this probability, and remember this is for x. X is only a normal random variable, not a standard one. Table 3 in appendix C tells you the values of a standard normal one. And so we have to translate this probability into a standard normal probability. Okay. So thus to find that probability, we do the following. The probability that A is less than capital X less than B is equal to the probability that A minus mu over sigma is strictly less than X minus mu over sigma, which is strictly less than B minus mu over sigma. Okay, so all I did was this original inequality, these original two inequalities, I took each term, subtracted it by mu, and divided by sigma. And so that preserves the order of the inequalities. And so if I take each of these things, subtracted by mu, and divide by sigma, the first thing is still less than the second thing, and the second thing is still less than the third thing. Okay? And so the reason why I did this was because now the middle term is x minus mu over sigma, which we said was z, where z is a standard normal random variable. So this is the probability that a minus mu over sigma, this is a constant, is less than z, which is less than b minus mu over sigma. So now this is the probability that a standard normal random variable is in this range. And so now we can take this problem and we can translate it, and so now we translate the problem of finding the probability of a normal random variable to finding the probability of a standard normal random variable. And so for this, you would use table 3 in appendix C of the book, the course, to calculate this probability. Okay, so the table the table in Table 3, Appendix C, does not calculate the original probability because, again, x is only a normal random variable. Table 3 in Appendix C is for a standard normal random variable. And so, again, what we did was we took this probability in terms, the probability of a normal random variable, and set equal to a probability of a standard normal random variable. And then use the table for this to find this, and then you found your original probability. Okay? And so this is the method you need to use to find the probability of a normal random variable x. Okay? And so in the next example, we'll use this method to get the answer to the next example. Okay, so I'll leave that for a moment on the board. It's good if you copy this down because then this is like a summary of what you need to do. Okay, let's keep going. Okay, so the next example is 5.16. Okay, so example 5.16. So let capital X be a normal random variable with parameter mu equals 2 and sigma equals 0.5. Find the probability that 1 is less than x less than 2.1. Okay. And so we're just going to use the method before. So this is the solution to exercise 5.16. The probability that 1 is less than x less than 2.1 is equal to the probability that 1 minus mu over sigma is less than x minus mu over sigma, which is less than 2.1 minus mu over sigma. So I'm going to take, just like on the method I showed in the previous board, I'm going to take each of these things, subtract by mu, and divide by sigma. Okay, and so that's equal to the probability that 1 minus mu over sigma is less than z, where z is that. So z is going to be equal to x minus mu over sigma, and z is a standard normal random variable, and that's less than 2.1 minus mu over sigma. So z here is a standard normal random variable. Okay, so we add the word standard now for this one, because it's of the form x minus mu over sigma, where x is a normal random variable. Okay, so we're given that mu is 2 and sigma is 0.5, and so you just plug that in. So it's probably that 1 minus 2 over 0.5 is less than z, less than 2.1 minus 2 over 0.5. And so that's equal to the probability, this is negative 1 over 1/2, which is negative 2. The probability negative 2 is less than z, less than 0.1 over 0.5 is 0.2. Or 1/5. Say 0.2. Because 2.1 minus 2 is 0.1. 0.1 divided by 0.5 is 1/5. 1/5 as a decimal is 2/10, or 0.2. Okay, that's 0.2. So there's a probability that z, our standard normal random variable, is between negative 2 and 0.2. And so that's equal to the probability that negative 2 is less than z, less than 0, plus the probability that 0 is less than z, less than 0.2. By symmetry, that's equal to probability 0 is less than z, less than 2, plus the probability 0 is less than z, less than 0.2. Okay? So from negative 2 to 0.2 is the same as from negative 2 to 0, and then from 0 to 0.2. And from negative 2 to 0 is the same as 0 to 2 by symmetry, and then plus the same thing. And so you find the probability of this, and you find the probability of that in table 2 in Appendix C. Okay? So this probability and this probability you find their probabilities. Use table 3 in appendix C to calculate, to find them. You're not calculating, you're finding them in the table. And so you plug in this probability and that probability and you add them and you get the sum. The final answer is 0.5565. Okay, so the final answer is 0.5565. That's the probability that 1 is less than x less than 0.2.1. Okay, and so we did use the method on the previous board to find that probability. This probability is equal to that. Let's keep going. Okay, so next example is 5.17. Okay, suppose any given day's gross receipts in thousands of dollars. From a certain sales unit, may be treated as a normal random variable. X with parameters mu is equal to 20 and sigma is equal to 2. Find the probability that A, the gross receipts, and so I'm just going to write this probability of the gross receipts are between $15,000 and $25,000. Okay, so we want to find this probability, the probability that the gross receipts are between $15,000 and $25,000. So let's read the problem again. Example 5.17. Suppose any given day's gross receipts in thousands of dollars from a certain sales unit may be treated as a normal random variable x with parameters mu is 20 and sigma is 2. Find the probability that probability. Okay. Okay, so capital X is any given day's gross receipts in thousands of dollars from a certain sales unit may be treated as a normal random variable, capital X. So that means the gross receipts here, in thousands of dollars is X, but it's between 15 and 25. So it's a probability that 15 is less than X, less than 25. Okay, X is the given day's gross receipts in thousands of dollars, and it's between 15 and 25. Okay, probably 15 is less than X, less than 25. Now we're going to use the same method as before. We're going to take this 15 minus mu over sigma less than X minus mu over sigma less than 25 minus mu over sigma. Okay, we're taking this probability of a normal random variable and we're going to translate it to the probability of a standard normal random variable. Okay, so that's our standard random variable z. So this is equal to the probability that 15 minus mu over sigma is less than z, less than 25 minus mu over sigma. Where z is x minus mu over sigma, and z is a standard normal random variable. Okay, that's a standard normal random variable z. And so now we are given mu is 20 and sigma is 2. That's mu and that's sigma. And so you just plug those values in. You get 15 minus 20 over 2 is less than z, less than 25 minus 20 over 2. And so the probability is that the z range is somewhere there. So 15 minus 20 is negative 5. Negative 5 over 2, less than z, less than 25 minus 20 over 2, which is 5 over 2. So the probability that z ranges from negative 5 over 2 to 5 over 2. That's equal to the probability that negative 5 over 2 is less than z, less than 0, plus the probability that 0 is less than z, less than 5 halves. Okay, so you can split the integral from negative 5 halves to positive 5 halves. So you integral from negative 5 halves to 0, and then from 0 to 5 halves. And then by symmetry, you can switch that. So that's equal to the probability that 0 is less than z, less than 5 halves. Right, so this probability is equal to that one by symmetry, plus, reflect it, right, okay, plus the probability, the same probability, that 0 is less than z, less than 5 halves. And so you're adding the same probability to itself twice. And so this is equal to 2 times the probability that 0 is less than z, less than 5 halves. And this is equal to 2 times that probability, which by the table is 0.4938. And that's equal to 0.9876. Okay, so that's 0.9876. So this probability, I'm just going to put brackets here. Okay, so you're adding this probability to itself. So it's 2 times that probability, which is 2 times 0.4938. That's in the bracket there. 2 times that is 0.9876. Okay, and then that's the probability you need to find for part A of the problem. Okay, so let's keep going. That's A. Okay, so part B. Okay, so part B is probably of the gross receipts are more than $24,000. Okay, so for part B, you want to find the probability that the gross receipts are more than $24,000. Okay, so X is the amount of gross receipts in thousands of dollars. So this is the probability that X is greater than 24. Okay, so I'm going to translate this as probability of a standard normal random variable by doing X minus mu over sigma is strictly greater than 24 minus mu over sigma. That X minus mu over sigma, that's Z. This is the probability that Z, which is X minus mu over sigma, is greater than 24 minus mu over sigma. And so this is equal to the probability that Z is greater than, and I'm going to plug in mu and sigma, it's 24 minus mu, which is 20, over sigma, which is 2. So that's probably Z, our standard normal random variable, is greater than 24 minus 20 over 2. That's equal to the probability that Z is greater than 24 minus 20, which is 4. 4 over 2 is 2. That's the probability that Z is greater than 2. So what's that probability? Well, that's equal to 1 minus the probability that Z is less than or equal to 2. That's equal to 1 minus the probability that Z is less than 2. You can get rid of the equals there. Right? Probability that Z a continuous random variable takes on any one particular value, 0, so you can remove the equals and just be strictly less than 2. That's equal to 1 minus, now the probability that z is less than 2 is the probability that z is less than or equal to 0 plus the probability that 0 is less than z less than 2. Right? So when it's less than 2, it's either less or equal to 0 or between 0 and 2. And those two events are mutually exclusive. And so the sum of those probabilities is the probability of the union, which is that. And so this is equal to 1 minus, the probability is z less or equal to 0. Z has symmetry about the mean, mu, which is 0, because it's a standard normal random variable. So this is 1/2 here. So that's 1/2. This probability z is less or equal to 0 is 1/2. And so that's 1/2 plus this probability. And for this one, you use the table. Okay? And so the table tells you that that's, I'm going to put 1/2 as 0.5. Okay? So that's 0.5. And it's plus this probability, which you get by the table, which is 0.4772. Okay? So it's 1 minus that. So that's equal to 1 minus 0.5 plus 0.4772, which is 0.9772. And so 1 minus 0.9772 is 0.0228. That's the answer. Okay. And so the probability that the gross receipts are more than $24,000 is 0.0228. It was the probability that x, which was a normal random variable, is greater than 24, which equals to the probability that z, which is a standard normal random variable, is greater than 2. And then use the appendix and this fact to know this is 1/2. And you calculate this in the appendix, you know this is 1/2. And then 1 minus that sum is 0.0228. Okay? So here's another example of that method of finding the probability of a normal random variable using the appendix to find probabilities of a standard normal random variable. Okay? So we've seen a few examples of this method. Right? X minus mu over sigma. So we keep doing. Okay, so that's the end of chapter 5. Let's keep going. Okay, so that's the end of chapter 5, and let's go to chapter 6. Chapter 6, the title of chapter 6 is Mathematical Expectation. Okay, so this chapter is on mathematical expectation. 6.1 is titled the mathematical expectation of a random variable. Okay. And 6.1.1 is an introduction. Okay, and so basically the most important number associated with a random variable is the expected value. Okay, so this ends up being the most important number to study a random variable, its expected value. You can learn a lot about it by knowing its expected value. Okay, 6.1.2 is the mathematical expectation. E of x. Okay, so let's define what this is. This is definition 6.1. And so the mathematical expectation of a discrete random variable capital X with probability function to the left of x is the quantity E of x is equal to the sum over x of x times f of x, provided that the sum over x of the absolute value of x times f of x is finite. So the series converges absolutely. Okay, so this is the definition of the mathematical expectation of a discrete random variable x with probability function little f of x, a long name. Okay, so the mathematical expectation of a discrete random variable x with probability function little f of x is the quantity capital E of x is equal to the sum over x of x times f of x, provided that the sum over x of the absolute value of x times f of x is finite. So the series converges absolutely. Okay, so that's the definition. This sum, which is saying is finite, what that means is saying a series or sum converges absolutely means that if you take the original sum, but instead of adding the terms of the sum, you add the absolute value of those terms. If you get a finite number, when you add up these infinitely many terms, the terms are this, x times f of x for this sum. If you take the absolute value of each term, you add up the absolute values. If you get a finite number, then the original series converges absolutely. So this series, capital E of x, converges absolutely if the sum of the absolute value of the terms is finite. Okay, and so that's what's happening here. F of x is the probability function, and so f of x is never negative. And so the absolute value of f of x is itself. And so taking the absolute value of x times f of x is just the absolute value of x times f of x. And so that's why when we talk about this, making this series converge absolutely, which is the sum of the absolute value of the terms, the absolute value is only around x, not x times f of x, because since f of x is non-negative, the absolute value of it is equal to itself. And so we don't need the absolute value there, we only need it around the absolute value of x. So the absolute value of x times f of x is the same as the absolute value of x times f of x. Okay? And so finding that this sum is finite is saying that this series converges absolutely. And that's the condition in order to say that this sum is the mathematical expectation of a discrete random variable x. Okay? So again, it's saying that E of x, the mathematical expectation of a discrete random variable capital X with probability function little f, that E of x is equal to that sum as long as the sum of the absolute value of its terms is finite, is a finite number. Okay? And that's represented by that, where the absolute value is only around x, because f is positive or 0, it's not negative. So the absolute value of it is equal to itself. Okay? Okay, so that's the condition of saying that that's equal to that sum, that the sum of its absolute values is finite. Okay, and that's the definition of the mathematical expectation of a random variable. Okay, also this sum over x denotes the summation over all values of x that are possible values of the random variable capital X. So where should I write that? So I'm going to write this over here. The sum over x part, this thing here, right? This part here, the sum over x, this thing over there denotes the sum over all values little x of the random variable capital X of x. Okay, so this sum, that sum, the sum over here over x, that notation means we're denoting the sum over all possible values little x of our random variable capital X. Okay, so if capital X only takes on values of -1, 1, and 0, then we're only summing over values of little x of -1, 1, and 0. Okay? So this sum could be over an infinite number of x's or finite, right? Capital X is a random variable. It could be, it's discrete. So it's a discrete random variable. That means it's either finite, that means the possible values of that little x could take is finite, or if capital X is discrete, infinitely discrete, discrete is an infinite set, it's a countable set, countably infinite, that means that you could sum over infinitely many values of little x, values that are one-to-one correspondence with the positive integers, okay? So this sum could be infinite or it could be finite, okay, depending on what type of discrete random variable x you have. But the sum is always the sum of all possible values of little x that capital X takes on. Okay. The number of possible values of x is limited by the fact that it's a discrete random variable. Okay. Okay. So that's the definition of E of x. And I'm going to put a note here. E of x is also denoted by mu. Okay? E of x is also denoted by mu. So mu could be used instead of capital E of x. Right? Okay, so the mu in the previous formula for our standard normal random variable and our normal random variable, that mu is E of x. But you didn't need to know that at that point. It was just a letter, a parameter. But it turns out it's this E of x. Okay, so E of x is also denoted by mu. So instead of using that symbol, I could use mu instead. Two different notations for the same thing. Okay, so we now have the definition of E of x or mu out of the way. So let's do an example. Example 6.1. Let capital X be the numerical outcome of one roll of a die. Find E of x. Okay, so example 6.1. Let capital X be the numerical outcome of one roll of a die. Find capital E of x. Okay, so solution. So you have a roll of a die. So I'm just going to draw a die so we can visualize, right? The numbers on the die range from 1 through 6. So those are the possible values of x. So x could equals 1, 2, 3, 4, 5, or 6. Little f of x, the PDF of capital F of x, is equal to 1/6 for each value of x. So that it's 1/6 for x equals 1, 2, 3, 4, 5, or 6. So that's the PDF. Right? By the definition of the expected value, capital E of x is the sum over all possible values of x times f of x. And so what is that equal to? That's equal to 1 times f of 1 plus 2 times f of 2 plus 3 times f of 3 plus 4 times f of 4 plus 5 times f of 5 plus 6 times f of 6. Okay? And so summing over all possible values of x times f of x, well, all possible values of x are 1 through 6. And so you're just going to take x times f of x when x is 1, 2, 3, 4, 5, or 6, and then you're going to add up those terms. So that's when x is 1. That's x times f of x when x is 1. That's x times f of x when x is 2. That's x times f of x when x is 3. That's x times f of x when x is 4. That's x times f of x when x is 5. And that's x times f of x when x is 6. And so you find each of those terms for each value of x, and then you add them up. Right? Well, f of any value of x is 1/6, and so each of these f values is 1/6. So this is 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 plus 4 times 1/6 plus 5 times 1/6 plus 6 times 1/6. Okay, and so you add this up, and you get it's 1/6. I'm going to factor out the 1/6. This is 1/6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. Okay? There's a formula that says the sum of the numbers from what. You don't have to know this formula, you could just add them. If you want to know the formula, it's 1 plus 2 plus dot 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 plus n is equal to n times n plus 1 over 2. That's a shortcut. So for instance, the sum of the numbers from 1 to 6, the integers from 1 to 6, n would be 6. And so that'd be 6 times 7 over 2. That'd be 21. And so the sum of the numbers from 1 to 6 are 21. So that'd be 1/6 times 21, and that would be 7/2, which is 3.5. And so the E of x is 3.5. Right? So that's just a shortcut. So, right, so applying that shortcut to here, it would be 1 plus 2 plus dot 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 plus 6 is equal to 6 times 6 plus 1 over 2. That's 6 times 7 over 2. That's 3. 6 over 2 is 3. 3 times 7, which is 21. So the sum from 1 to 6 is 21. Okay. So if it was the sum from 1 to 10, it'd probably be worthwhile to do it, because the sum from 1 to 10 would be 10 times 11 over 2. And that'd be 55. So it's faster to do it with a formula. But if you don't know the formula, you can just add it. And get 7 plus 7 plus 7, which is 21. And you take the outer 2. 1 plus 6 is 7, 2 plus 5 is 7, and 3 plus 4 is 7. You get 3 7s, and it's 21. 7 plus 7 plus 7, 7, 14, 21. And the sum is 21. 1/6 times 21, 7/2, which is 3.5. Okay, and so that's the solution. The expected value E of x is 3.5. Okay, so let's do the next example. Right, the sum of the numbers from 1 to 100 is 100 times 101 over 2. So 50 times 101, which is 5,050. It's number 3. Okay. So this is example 6.2. Let x be a discrete random variable with a probability function f of x, which is equal to 1/3 for x equals 3, 2/3 for x equals 9. Find the expected value E of x. Okay, so we're given the PDF, the probability density function f little f of x, and you can also see what all the possible values of little x are. When x is 3, the probability is 1/3. When x is 9, it's 2/3. these probabilities add up to 1. And so there can't be any other non-zero probability of x being a different value. Those are x equals 3 and x equals 9, the only values x can take. So let's find capital E of x. Solution. Capital E of x is equal to the sum over all possible values of x times f of x. And the possible values of x are x equals 3 and x equals 9. And so this is 3 times f of 3 plus 9 times f of 9. So this is equal to 3 times f of 3 is 1/3 plus 9 times f of 9, which is 2/3. So 3 times 1/3 is 1. 1 plus 9 times 2/3 is 6. So 1 plus 6 is 7. And so capital E of x is 7. Okay. So capital E of x is 7. Good. So this is a good example to see to find E of x. It's short. It's shorter than the other one. It's easier. Okay, and so the next definition. Definition 6.2. The mathematical expectation of a continuous random variable capital X with probability density function to f of x is the quantity capital E of x, which is equal to the integral from negative infinity to infinity of x f of x dx, provided the integral exists. Provided the integral exists. Okay, so definition 6.2. The mathematical expectation of a continuous random variable capital X with probability density function low f of x is the quantity capital E of x, which is that integral provided the integral exists. Okay. This is the definition of the mathematical expectation of a continuous random variable capital X. Is the because it's unique. Okay. Right, it's still x times f of x, but instead of taking the sum of all possible values of x, it's an integral, an improper integral from negative infinity to infinity. Okay, example 6.3. Let capital X be a continuous random variable with probability density function little f of x is equal to 81x squared for 0 less than x less than 1/3, 0 elsewhere. Find capital X. So let capital X be a continuous random variable with probability density function little f of x, which is that. Find capital E of x. Okay, so we're just going to use this definition. Capital E of x is equal to that integral, provided the integral exists. right? Important to note. This is provided the integral exists. So if the integral doesn't exist, you did not find e of x with that integral. It doesn't have an expectation. Okay, so capital E of x is equal to the integral from negative infinity to infinity of x times f of x dx by the definition. Okay, so that's by the definition of the mathematical expectation of a continuous random variable capital X with probability density function of x. Okay, now little f of x is 0 everywhere other than this interval, right? Well, outside this interval, little f of x is 0. So if little f of x is 0 everywhere outside of that interval, that means the integral is 0 everywhere else. So this is equal to the integral from only 0 to 1/3 of x times f of x, which is 81x squared there, dx. And so we can, instead of finding the integral from negative infinity to infinity, in this case, you only need it from 0 to 1/3 because that's the only place where the integrand, x times f of x, is non-zero. Because that's the only place where f of x is non-zero. And so I'm going to move the 81 out of the integral. So this is 81 integral from 0 to 1/3 of x cubed dx. So x times x squared is x cubed. 81 moves out of the integral, so it's 81 times that integral from 0 to 1/3. And so that's equal to 81 times x to the 4th over 4th, which is an antiderivative of x cubed, evaluated from 0 to 1/3, right, by the fundamental theorem of calculus. This definite integral is equal to x squared over x to the 4th over 4, evaluated from 0 to 1/3. That's 81 times, plug 1/3 in, you get 1/3 to the 4th power divided by 4, minus plugging in 0, 0 to the 4th over 4. And so 1/3 to the 4th power is 1 over 81 divided by 4, which is 1 over 324. So this is 81 times minus 0, which is 1 over, what did I say, 324? I'm going to have to check. 81 times 4, which is 324. So 81 times 1 over 324, that's divisible by 3, so is 81. So this is 81 over 324. And so actually it's 1/4. 81 over 324 is 1/4, and so that's 1/4. Okay, so E of x is 1/4. 81 times 4 is 324, so 81 over 324 is 1/4. Okay, so I wrote out all the steps here. Okay, good. Okay, so that's example 6.3. Okay, so again, this is the only place where the integrand is non-zero, and so I restricted. You don't have to compute the integral from negative infinity to infinity. Instead, it's from 0 to 1/3. Right? I moved the 83 out. X times x squared is x cubed, and then I just used the fundamental theorem of calculus to calculate this definite integral, which is 1 over 324, and multiply it by 81. 81 over 324 is 1/4. That's the definition before the example. Okay, so let's keep going. Next, 6.1.3. Why capital E of x is called the mean of x. What question mark? Right, so why capital E of x is the mean of x. So let's look at this example that illustrates it. Example 6.5. Okay, so we have a class of capital N students is given a test. possible grades are A, B, C, D, and F, with numerical values, with number values, 4, 3, 2, 1, and 0, respectively. Suppose we choose a student at random from the list, from the class, and let capital X equal the number grade received by student. Chosen. So capital X is the number grade received by the student chosen. What is capital E of X? Okay, so the question is, what is capital E of X for this problem? Put the solution there. Let me read the problem from the beginning again. Example 6.5, a class of capital N students is given a test. The possible grades are A, B, C, D, and F, with number values 4, 3, 2, 1, and 0, respectively. So A is a 4, B is a 3, C is a 2, D is a 1, and F is a 0. Suppose we choose a student at random from the class and let capital X equal the number grade received by the student chosen. What is capital E of X? Okay. Okay, and so let's find it. Okay, let capital N sub X equal the number of students with number grade little x. Then little f of x is n sub x over capital N, for little x is equal to 0, 1, 2, 3, 4. Okay, so what does that mean? Capital N sub x is the number of students with a number grade of little x, right? So if you have a class of capital N students, and you want to ask yourself, how many students got an A, right? That would be the same as saying, how many students got a number grade of 4? So capital N sub 4 would be the number of students with a number grade of 4. And so capital N sub 4 is the number of students who got a number grade of 4, or the number of students who got an A. And so if you want to know the probability that when you chose a student at random from this class of capital N students, with the probability that that student received a grade of 4, it would be the number of students that got a 4 out of the total number of students. And so capital N sub 4 would be that number, the number of students who received a 4, divided by capital N, the number of students in the class. But instead of writing N sub 4, I wrote N sub x for x from 0 to 4. And so this represents the probability for each value of x. So little f of x is the probability that is the probability of any number grade, 0, 1, 2, 3, or 4. Okay, and so now we have our PDF. And so since we have our PDF, let's find E of x. So let's find the expected value. The expected value is the sum over x of n sub x over capital N. It's a sum over all possible values of little x. Those possible values are from 0, 1, 2, 3, or 4 of n sub x over n. And so this is equal to, since capital N in the denominator is the same, if you're adding a bunch of fractions where they have the same denominator, capital N, then you could instead add the numerator add the numerators, and divide it by the common denominator. Right, the sum of those fractions is equal to the sum of the numerators divided by the common fraction of capital N. So this is the sum over x of n sub capital X over capital N. Oh, wait, sorry. Oh, well, I just forgot something. Okay, this is x times f of x. So since it's x times f of x, it's the sum over x of x times f of x, which is n sub x over n. Okay. So little f of x is this, right here. And so it's still the sum over x. The common denominator is capital N, so it's the sum over x of x times n sub x over capital N. Right? So you can think of x times n sub x over capital N as x times n sub x divided by capital N. And so you're adding up fractions with the common denominator of capital N, and so you can instead add the numerators and divide it by the common denominator of capital N. So it's the sum over x of x times n sub x divided by capital N. Well, so what does this represent? This sum over x of x times n sub x is adding over all possible number values. It would be taking the number of students who received a grade and multiplying it by that grade. Okay, so for instance, n sub 0 would be the number of students who received a 0 times 0. N sub 1 would be the number of students who received a 1 times 1. And then plus n sub 2, the number of students who received a 2 times 2. And so adding this all up is the sum of the grades. This is the sum of the grades divided by the total number of grades, because it's n students. Total number of students. If you take the sum of the grades of the students in the class and divide it by the total number of students, you get the average grade. Okay, so that's the average grade. So here in this example, capital E of x is equal to the average grade a student gets in the class. Okay? So again, this sum is the sum of the grades of the students in the class. And E of x at the end is an average grade. So I'm going to put a box here. Capital E of x is an average grade. The numerator is the sum of the grades. Okay, so here we found, capital X is the average grade of a student gets in the class. And so this is illustrating why capital E of x is the mean of capital X. Okay? We can see how it relates to the average as we normally think of it. Okay, so it's not always precisely the average, and so we have to be more precise than just saying it's not necessarily the same as the normal average you think of. In this example, it's the average, but in other examples, instead of getting the average, you could get the average of the values weighted by the frequencies. Okay, so let me. Right? So you wouldn't necessarily just take the average of the values of x. It would be the average weighted by the frequencies of the values of x. So let me write that down. So technically, the mean of capital X is interpreted here as the average of the values of capital X weighted by their frequencies. Okay, so the mean of x is interpreted here as the average of the values of x weighted by their frequencies. Okay, so what do I mean by that, right? So even in the last example, if you have a class of 100 students, right? And again, that class could get number grades of 0, 1, 2, 3, or 4, right? Those are the possible values of x as a grade, right? Now, it's not the average value of x. The average value of x would be the average of the numbers from 0 to 4. And so if you took the average of those numbers, you add them up, you get 10 divided, you get the average is 2, right? So the average of these numbers, the average of 0, 1, 2, 3, and 4 is 2, right? If somebody just gave you the numbers 0, 1, 2, 3, and 4 and said, what's the average of them? It's 2. But the average grade in a class is not the average it's not the average of the given possible grade values, right? It's weighted by how many students get each grade, right? And so when you take the average of the average grade of 100 students, you're not going to always get 2. It's not always going to be the average of the possible grades. It usually won't be the average of the possible grades, right? Right? If a normal test is from 0 to 100, if you give a class of 100 students a test, and you say, what is the average of the possible grades? You would say 50, right? It's in the middle. But the average grade in the class is not usually 50. You're weighting the grades by how many students got each grade. So that's what it means. The mean of x is interpreted here as the average of the values of x weighted by their frequencies, right? And so we're not treating each grade as being equal. Grade of 0 is not the same as the grade of 4. It's not the same as grade of 3 or 2, right? Maybe we weight 3 more than we weight 4. Maybe more people would get a 3 than they would get a 4, right? And so it's not the average of possible grades. It's the average of the grades weighted by their frequencies. Weighted by, in this case, how many students got each grade. Okay, so that's really the meaning of the mean of capital X. Okay. So let's look at another example. Example 6.6. So example 6.6, show if capital X is a number selected at random. So if x is a number selected at random from a finite set capital A of numbers, from a finite set capital A of numbers, then capital E of x and capital E of x is the mean of the set capital A of numbers. Okay, so example 6.6. Show if capital X is the number selected at random from a finite set capital A of numbers. Then capital E of x is the mean of the set capital A of numbers. Okay, so let's do that. Let's call it proof. Okay, so assuming capital X is the number selected at random from a finite set capital A of numbers, then E of x. Okay, so let let capital A equal A1, A2, dot dot dot, A sub n, such that A sub I is a number for 1 less than or equal to I less than or equal to n. So A sub I is a number from 1 to n. That means that each of these A's are numbers, A1 to AN. That's what that notation is saying, that those A's in the set capital A are numbers. Okay, and so f of A sub I is equal to the probability that capital X equals little a sub I, and that's equal to k sub I over n for I equals 1 to up to including little m, where k sub I is the amount of values in set capital A that equal a sub I. Okay, so f of a sub I is the probability that capital X is equal to a sub I, right? Now that's equal to k sub I over n for the i's from 1 to m. That means that k sub I is the amount of these values that equals a sub I. Right? So the probability that x is equal to one of these values is the amount of values that are the same as it in the set divided by the total number of values in the set, which is little n, because it goes from a1 to an. So since the subscripts go from 1 to little n, there's little n of them in the set. Okay? And so again, the probability that x is equal to a sub I is the number of values in the set that are the same as a sub I divided by the total number of values in the set, which is little n. And this is for any I from 1 to little m. And it's little m because even though there's little n values in the set, some of them are the same. And so there's little m different. Little m is the number of different values in the set. Okay? And so little m is the number of different values in the set. Little m is the number of different values in the set. Okay, so e of x, let's say we arrange the a's. Let me just say, we arrange the a's so that if you chose the first little m of them, they will be different, and then the rest of them are the same as the first little m, okay? And so that's how we arrange this set capital A. So capital E of x is equal to the sum from I equals 1 to little m of x sub I, f of x sub I. And this is equal to the sum from I equals 1 to little m of x sub I times f of x sub I, which is k sub I over n. So this is equal to the sum over I equals 1 m of x sub I, k sub I divided by n. Okay, and so so the possible values of x sub I are one of the a's. Right, x is a number selected at random from the finite set capital A of numbers. So the possible values of x sub I, right, are from here. It's the first m of them that are different, which are the same as the rest of them. Okay. Well, okay. Let me explain what I mean. We're going to order the set capital A. We're making the order from A1 to AN, just that A1, A2, dot 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 to A sub m are the different ones. And so if you have n values that can repeat, then there's exactly m different values in the set where m is less than or equal to n. And so we're going to arrange it so the first m are different, and then the rest of them are the same as one of the first little m that were different. Okay, so that's how the set is arranged. The first m of them are all different, and then from m plus 1 to n, the rest of them, each of them are the same as one of the first little m values that are different. And so there's little m many different values that x can take. And so k sub I is the number of values that are the same for each one of these. So k sub 1 is the number of values that are the same as a sub 1. K sub 2 is the number of values that are the same as a sub 2. Dot dot dot. K sub little m is the same as the number of values that are the same as little a sub m. Okay, and that's all the different values, and then the rest of them are the same. Okay, and so it encompasses all the ones in the set. Okay, so the sum from I equals 1 to little m of x sub I times k sub I means, so we're taking each possible value, different value in the set A, and then we're multiplying that value times the number of times it appears in the set, and then we're adding the sum. And so this numerator is the same as the sum over all possible values in the set. So this is the same as A1 plus A2 plus dot 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 plus A sub n, the sum of all of the values, divided by little n. Okay, and this is equal to the mean of the set capital A of numbers. Okay, so the conclusion we want to reach was that E of x is the mean of the set capital A of numbers. And what we showed is that E of x is equal to the mean of the set capital A of numbers. And so we proved that. And so we're done. Okay, and so that's example 6.6. That's the end of the proof. Okay, so thanks for watching the video, and I'll see you the next one.